Alright, so this is just I was asked to do one of the stoichiometry problems, limiting reactant, percentage yield, that sort of thing. And so what I've done is to start putting it together here. I've just written it out like this: 2 grams of barium chloride dissolved and mixed with an equal concentration of sodium sulfate, 1 gram of solid product collected. What's the percent yield? So I'm writing a balanced equation here. It says that the sodium sulfate has an equal concentration. Well, that must mean it's also aqueous. We could look it up on the solubility rules, and we'd find that group 1 metal compounds, like sodium sulfate, are aqueous. So this would be aqueous. And then we want to predict the products. Since I have 2 ionic compounds, and we know this one's ionic, the shortcut way of figuring that out is this is a metal or non-metal. That's usually almost always going to be an ionic compound. This compound contains this polyatomic ion. If you don't recognize it, you can look at the list of common ions we use in this class and see that sulfate is a polyatomic ion, therefore this is an ionic compound. When you put 2 ionic compounds together, if there's going to be a reaction, it's almost always going to be double replacement. Not every time. There are lots of exceptions. So, but in this case, that's what the first thing you would predict. So if it's a double replacement reaction, the front part of this has got to go with the back part of this. So barium has to be put with sulfate. Now notice the only subscripts I'm carrying over are those that are part of a polyatomic ion. Okay? I'm not going to carry over this subscript or this one because these 2 subscripts here and here are not part of a polyatomic ion. I carried this one over because it is part of a polyatomic ion. So the phrase we use is it doesn't travel unless it's part of a polyatomic ion. And let's see, so we're going to put sodium with the chlorine, and we're just going to put sodium and chlorine, not Na2Cl2. Just 1 sodium and 1 chlorine because those subscripts don't travel. We need to figure out the physical states of these products now, because when we're done, we need to know what the solid product is. All the problem tells you is that there is a solid product. It doesn't identify it. So that's where we are going to need the solubility rules. And in the solubility rules, we can see that all group 1 salts are soluble. So if there's water, a soluble compound will be aqueous. Also, chlorides are soluble, with the exceptions of silver, lead, and mercury compounds. And this is not a silver, lead, or mercury compound. So there's actually 2 rules that apply to this and tell you that it's aqueous. So let's see if we can find something in our solubility rules that applies to this compound. We'll go down here to sulfates. That's what that is. And see that sulfates are soluble except when they're bonded with calcium, strontium, or, and there's barium. And that's what we have. So this is a barium sulfate. It's an exception. Most sulfates are soluble, but barium sulfate is not. So this is going to be a solid. There's our solid. Okay? All right. Yes, sir. There's a pencil sharpener under the Y's out on the back. So we're going to now list all of our elements in an atom inventory. Okay, Ba, Cl, Na, S, and O. And we're going to make this sort of grid or spreadsheet here. And we're going to count all of the elements we have.
Atom inventory.
Atom inventory.
Yeah.
1 barium, 2 chlorines, 2 sodiums, 1 sulfur, 4 oxygens. Okay. Over on this side, I have 1 barium, 1 chlorine, 1 sodium, 1 sulfur, 4 oxygens. Okay?
Yeah.
All right. So what we need to do is to get everything to be equal on both sides. And we always save oxygen for last. Of course, in this case, it's already balanced. But the first thing I see on this list that isn't balanced is the chlorine. Now, once these formulas are balanced, we have to leave them alone. Can't touch this.
Can't touch it.
That's right.
Do-dum.
Yeah, okay. Now, so what we can use to balance the equation are coefficients, big numbers out in front that applies to everything in the formula.
Yeah.
So by putting this 2 here, we are going to get 2 chlorines over on this side. We're also going to get 2 sodiums, and that balances the equation. Okay? All right. Now, this is the kind of problem where turning your paper sideways probably helps a lot. So I'm going to go to a different sheet of paper just to start doing that. Here. Turn it sideways because it kind of gives us a long problem. Now, you can do this as this this next calculation as 3 separate problems if you want to, but I like to do it as one because it just kind of speeds things up.
Right.
Okay?
Right.
So slide this problem underneath here. Okay, so we can kind of keep up what's going on. All right. Okay. So we want to start with one of the 2 reactants, and if you read and interpret the problem, the 2 reactants are clearly barium chloride and sodium sulfate, and we wrote them right here. We have to start with one of those 2, and which one you start with does not matter for this next thing. Okay, what matters is that you calculate from one to the other. And so both of them are starting with 2 grams. Well, I'm just going to pick the first one. Okay, so we're going to say 2 grams.
2 grams.
Of barium chloride. I'm going to put that over 1. So for most of the time, when we're doing stoichiometry, your starting amount always goes over 1.
Right.
The next step is to convert it into moles. But to convert it into moles, I need the molar mass. And I haven't calculated that yet, so we have to calculate the molar mass for barium chloride. All right, so to do molar mass, we're going to take and list all of our elements in the formula. Okay? And then we're going to go to our periodic table and find the atomic masses for these elements, such as barium being 137.327.
Yep.
And in the formula, I've only got one barium, so I'll multiply that times 1.
That equals the same thing.
I'm about to add all this up for you.
I can do it in my head.
And then chlorine, we have an atomic mass of 35.453.
Multiply that by 2.
Times 2, yeah.
Okay.
Get 208.233.
Well, we first need to find what multiplying this by 2
That's
is.
that step right now.
Okay, so we want to take out our calculators and
Yeah,
do
that's good.
35.453 times 2. Whoop. Times 2.
Oh,
70.906.
meower there.
Now you just add it up right now.
And now we're ready to add it up.
Yeah.
So we're going to add that 70.906 to that 137.327.
Now that's an answer.
208.233. And that's your final fourth and molar.
Okay, now that's the numerical answer, but it's not the complete answer. For this class, we have to round off if necessary. In this case, there are no empty slots to the right. So that's the rule we use in here for figuring out our significant digits when we're adding and subtracting, but we don't need to round off here. But we have to write the following. We have to say this is grams of barium chloride. And in this class, we also have to write that this is equal to 1 mole of barium chloride. This then is an equality statement. The equality statement is what we use then to build conversion units. Okay? So we want to write a conversion unit where the units and species on the bottom of this fraction are the same as what we started with over here. And what was that for?
500 seconds.
Miles.
Yeah, but
I hope that I'm hoping you're concentrating as strongly on what we're doing to get ready for the final exam as you are on the time clicking down to 500 seconds.
We are meow, Mr. Tedder.
208.233 grams of barium chloride.
We don't need that.
That goes on the bottom, and if I put 1 mole of barium chloride on the top, this fraction is equal to 1. Anytime you have the same two numbers that are equal, one on the top, one on the bottom, the fraction itself equals 1. So this is called a conversion unit. Unit meaning basically 1. But what it does is it allows us to cancel units and species without changing the value of the starting amount. I'm going to cancel grams just like we cancel x and y's.
Answer the meow math.
Cancel x's or y's in algebra, and the species can be done the same way. So now we're at moles. Please. That's enough right now, okay?
Sorry.
All right. This next thing we're going to do is they call a molar ratio. Now, this is not a conversion unit. It is a conversion factor, but it's not a unit because it's not going to equal 1. But since we're going to we started with this, we want to end up with this, at least in this first equation, this first calculation. We're going to put this on the bottom. And this can be 1 formula unit of these two things, or it can be 1 mole of those two things. If I've got 1 mole here, that makes a mole of those, and 2 moles of that. A mole is a counting unit, okay? So we're going to put 1 mole of barium chloride then on the bottom here. And since this is what we want to try to find in this first stage, we're going to put 1 mole, there's an implied 1 here, 1 mole of Na2SO4. Just as in algebra, we don't put 1x when we're doing algebra. We just say x. Well, that's the same thing here. There's an implied 1 there, even though there's not a 1 written there. So we're going to cancel out moles and barium chloride. And now we're at moles of sodium sulfate. Well, we cannot compare moles of sodium sulfate. We need moles, but we need to get it into grams to actually figure out what's going on, because we want to compare it to our beginning mass. So we're going to convert this into mass, and for that we're going to need another molar mass calculation. So for this we're going to put down sodium and sulfur and oxygen.
There's 3 for this one.
Don't we want to get barium sulfate?
What? Eventually, but first we got to find our limiting reactant.
We're not doing
So right now we're finding the limiting reactant. Okay?
Yeah, we figured something else right now.
So until we find out what the limiting reactant is, we're not ready to find the theoretical yield.
Not right now.
All right, so sodium on the periodic table is 22.989769.
Yeah, that's a mole.
Wait, Mr. Tedder, did
Yes.
I say in the problem that Na2SO4 or whatever has the same concentration? So wouldn't that mean that there would be the same moles or whatever?
Depends on how you're measuring concentration.
That's a very good.
That is a very good question. It could be. So I should have been more specific. Right?
So what did you mean then?
Well, in this case, I guess I meant percent concentration, in which case the mass would be the same for both. 2 grams. But I should have been more specific. You're absolutely right. Okay?
Boy.
So instead of an equal concentration, let's say an equal mass amount. How about that?
Yeah, let's try that now.
All right? That's a good analysis. All right. And then sulfur, our atomic mass is 32.065.
Sure is.
And oxygen is 15.9994. Now in this case, we do have some empty slots. Got an empty slot here in this column, an empty slot in these 2 columns here. Okay, which means our answer will have to be rounded off. But let's add these up now. Oh wait a minute, I've got to multiply. Sorry, got to do that. All right, so let's see, sulfur times 2, sodium times 2, sulfur times 1, oxygen times 4.
Oh, it's going to be a big number.
Could be. All right,
Not in terms of value, but in terms of
22.989269
yeah.
times 2, 45.978538. This is just times 1, so it's the same number. And then 15.9994 times 4, 63.9976. All right, so we still have those empty slots here. I'm using arrows because if I can't put zeros there, putting zeros there indicate that we have a degree of precision that does not exist. And in science, we care about things like precision. So now we want to add all these numbers up. So we got 63.9976 on the calculator screen at the moment. I'm just going to take that and add to the other 2 numbers, 32.065 plus 45.978538 and 142.041 138 is the answer on the calculator. But because we have 3 empty slots here in these columns to the right,
Yeah.
we don't worry about slots that are empty to the left, only to the right. We're going to underline these 3 digits and round them off. Okay? And so the answer we're going to have when we're done with rounding off is 142.041. And that also, just like up here, is going to be grams, in this case of sodium sulfate, equals 1 mole of sodium sulfate. Okay, so that gives us an equality statement we need for writing the conversion unit we need here. We want to match the units and species that we have on the top in this fraction. We want to match them here on the bottom, so this side of the equality statement goes to the bottom here. 1 mole Na2SO4, and then the grams go on the top, 142.041 grams of sodium sulfate goes on the top. Units and species cancel. Okay, and now we're ready to do the math. All right, so what we're going to do here is we're going to multiply everything across the top. So 2 multiplying times 1 just gives us the same answer. I'm going to leave out the ones. 2 times, let's see, 142.041, and hit enter. And now I want to hit a separate operation. So I hit enter to go ahead and find that answer, and then separately hit divide by 208. Again, just like multiplication, we don't have to divide by ones because it gives us the same answer anyway. So the answer I get here is 1.364250623. Now, multiplication and division, significant digit rules are a little different. With multiplication and division, we're going to look at the entire multiplication division problem. We're going to look at the measured or calculated numbers, and there are only 3, this one, this one, and this one, and look at the number that has the least number of digits. This one has the least digits. That's what we want our final answer to have when we're done.
Yeah.
This is a measured number. These 2 are calculated, and you only look at measured or calculated numbers. All these ones are counting numbers, and we don't use those for determining significant digits. So we want 3 digits, 1, 2, 3. Those are our significant digits. We underline everything else, and we use an arrow to show that we're rounding off. So our answer then is going to be 1.36. We have units of grams left and a species of sodium sulfate left. Okay. Now, this number is theoretical. It's not, you might say it's not real, but it tells us how much sodium sulfate I need to completely react with barium chloride. And as you can see, I have a lot, I need a lot less than I actually have. So what this tells me by doing this calculation is I'm going to have sodium sulfate left over. The barium chloride is going to run out first. The sodium sulfate is going to be left over. So sodium sulfate is the excess reactant, and barium chloride is the limiting reactant.
Oh, right, initiative.
So this then is, this is the excess reactant, and barium chloride is our limiting reactant.
Right.
Well, that's, excess reactant.
What is it for?
That's a little symbol that means therefore. Okay, all right. Now that works out really nicely for us because the first 2 steps and half of the third step are the same ones I'm going to use in the next equation. Okay, because this is our limiting reactant, and I need to start with the given amount of the limiting reactant to find the theoretical yield. This is how I'm going to start right here. I'm going to just rewrite that same stuff to begin this next equation. If it wasn't, we'd be starting with the given amount of sodium sulfate. Well, now we're going to start with the given amount of the limiting reactant, which is barium chloride. Okay. Now,
In this next step, the moles of barium chloride are still going to be 1, just like before. That never changes because our balanced equation shows one of them. But now we're trying to find not the other reactant, we're trying to find the solid product. And the solid product is barium sulfate. So on the top of this fraction, then I'm going to put barium sulfate. And there's an implied 1 there, and we can assume all these 1, 1, 1, 2s, those to be moles, so we can say this is 1 mole of barium sulfate on the top. Cancel the units here and species. Okay, so we're at the point now where we need another molar mass calculation, this time for barium sulfate. So we're going to list all the elements that are in barium sulfate. There's barium, sulfur, and oxygen. I've already looked up the atomic masses in the earlier problems up here, so I can just transfer those down, save myself a little bit of work. Okay, so in barium sulfate, we have 1 barium, 1 sulfur, and 4 oxygens. Okay, notice how I'm trying to keep all my digits lined up vertically, especially the decimal places, so I can keep up with the significant digits. And so 15.9994 times 4. Hey, I did. I could have just transferred this other number, couldn't I? How about that? Good look. Okay, and we've got 1 empty slot to the right. That's what, in order to know that, it's good to keep all those digits vertically aligned. I'm ready to add all these together now. Whoa, that's not good.
Oh, yeah, clear.
Guys, come on now, use yours.
Okay, now because we've got some digits or some empty slots to the right, not to the left, we don't worry about the left, only the right, for addition and subtraction, we've got to underline then that digit. We're going to round that off then to 233. This 6 is going to round the 9 up to a 10, which makes this a 9. But we have to keep that 0 there because that is a significant digit in that slot.
Oh, yeah. That always confuses me. I forgot about that.
All right, now we're ready to use that information for this equality statement information for this conversion unit. I've got moles of barium sulfate on the top here, so what I need on the bottom here are moles of barium sulfate. That's 1 mole there of barium sulfate. And then on the top, we're going to put the 233.390 grams of barium sulfate. And we're going to cancel the units and species. And plug in the calculator and plug the numbers in the calculator anyway.
Alright, let's do it. Gotta be out that time.
The final answer.
Not yet. We're not done with the final answer yet. We're getting close. Getting closer and closer.
Once we find this,
2 times 233.390. Enter. Then separately, then divide. So it takes that answer down here.
Don't write on your calculator.
208.233 divided by 1.
We don't have to divide by ones because ones just give you the same answer. Okay? So then that gives us an answer we're going to put here, complete answer, 2.241623566.
Right.
Okay? And then we want to look at our measured and calculated numbers, determine we need 3 significant digits again.
Is it 3 every time?
No. You have to look at the actual numbers. It happens a lot in chemistry because probably the most common balance we actually use has 2 digits after the decimal place. And we don't use, in the lab, a lot of times we don't use a lot of our chemicals. But you can't depend on that. You actually have to count your significant digits. So the question was, do we always have 3 digits? That is not true. So 2.24 then grams. We have left grams of barium sulfate. So that's what we're going to write down here. Okay? And that is now our theoretical yield.
They have to put the 3 dots.
No. Well, you could. It wouldn't hurt a thing if you did. You could say theoretical yield. Okay? I don't know if you can see that on the screen or not. All right, so the problem is asking if 1 gram of solid product is collected, what's the percent yield? So 1 gram of the solid product, and the solid product we figured out up here when we're doing the balanced equation is barium sulfate, is the actual yield. Okay? And calculating percent yield is a matter of putting the actual yield
Yeah, we can get our final answer.
over the theoretical yield.
Nope.
And then taking that answer and multiplying by 100. You always multiply by 100 to get a percent. And percent is always part over whole, and this is considered the whole. Okay, this is the maximum possible amount. Not possible to actually get there, but it's like, anybody doing calculus in here? You know what a limit is, right?
Algebra 3.
And then pre-calculus.
This is,
Algebra 3.
okay, when you get to calculus, this theoretical yield is like the limit. Okay,
Right.
you get infinitely close, but you can't actually get there. Okay? All right, so we're ready to do that math. Oh, before we do that, notice units are going to cancel. Percents are always unitless. So remember that. Keep up with your units and species every time, and if your units don't cancel, you did something wrong. Okay?
Is the BASO4?
Well, the BASO4 here will cancel. That doesn't always happen, but in this case it does. What I'm saying always, it doesn't always happen with percents, but the units should always cancel in percents. Okay? So 1 divided by 2.24, then multiply that answer by 100. Okay? And we get 44.64285714. We need to round that off again. Both these numbers have 3 digits. Both of them are, well, this is a calculated number here. That's a measured number. So we round that off, and we get 44.6%. Now, it's not enough to tell me percent. You got to tell me what it applies to.
There's no units left because they canceled.
Well, I understand that, but you still have to tell me what the percent applies to. The percent is, that's the percent yield in barium sulfate. Okay? You need to be clear and specific.